All right, good morning, everyone. Welcome back to Machine Organization and Programming. Today is Monday. We're having lecture 19 today, and we'll be discussing function calls. A couple of announcements as we get started. Please remember that the quiz for week 4 is now available, and it'll be available through Wednesday morning at 8 a.m. You get 2 tries. There's no time limit, and I hope this turns out to be a better learning tool for you guys than just a strict one-time only time limit kind of quiz. Let me know if you have any feedback about that. Next up, Project 3 is due tomorrow evening. That's Tuesday evening. And hopefully sometime around tomorrow evening or Wednesday morning, the next project, Project 4, will be released. All right, without any more, I'm going to jump in with a little bit of review to get us started. So I just want to take a look at accessing memory. We're going to be using the stack a lot today as we talk about function calls. We'll be putting stuff on the stack, we'll be taking stuff off the stack, and so just want a quick review how some of these things work. So over here in the orange color, I've got some registers, in green I've got some assembly instructions, and then in blue I've got some memory. I've got the memory addresses here and some values that are already stored in memory. And then on the right, comments if I have any that I need to make. Okay, so if I take a look at this instruction, if I'm moving a long piece of data to a double word piece of data from register EAX to ECX, this EAX is actually going to take the contents of the register, which is 0x100, and store that in the other register. So if we do that, that's going to be the result. 100 is now stored in ECX. All right, now the next instruction, if I put this in parentheses, the parentheses mean go to memory and look up whatever is in this address. So the source here, EAX, has the value 0x100. I'm going to go to this memory address, 0x100 right over here is at 42, and I'm going to store the 42 into ECX. So I'm going to click there, and there it is. Okay, and the other really common addressing form we're going to be working with today is this indexed or offset memory addressing model, where I'm going to be looking at something that's 4 bytes away from whatever is stored in the memory pointed to by register EAX. So I go to EAX, that's address 100, I go there, so I'm looking at address 100 over here on the right, and then I go 4 more bytes, end up at 104, and get the answer 35, and I store that, there it is, 35, in ECX. So today we're going to be looking at function calls, and for the idea of function calls fits into the overarching topic of control flow. So the basic default mode for control flow is sequential, where I'm going to be looking at one instruction, read it, I execute it exactly once, and then I go down to the second instruction. I read it, execute it exactly once, then move on to the next one, and I just continue like that. I do all the instructions one at a time, exactly once. Conditionals are going to be a way to get around that a little bit and skip over some steps if I want to. So they require that I have some sort of condition. I'm going to be looking at data in the program and then making a decision about whether I want to execute an if block or an else block, something like that. Iteration is yet another trick we can use to change the control of flow. This is going to let us, based on some sort of condition, decide whether we want to go back and execute a sequence of steps again, or just have a sequence of steps that we're going to execute like 0 or more times with a while loop. And both of those, conditionals and iteration, require some of the same kinds of decision making. Let me just click right here and we can talk about the features that we need in assembly and hardware to implement those statements. So we need a way to evaluate a Boolean statement. If we have an if clause, that's got a condition in there. I need to know whether I want to take a particular branch or not based on that Boolean operator. So assembly is going to provide us with the compare and test instructions. Compare will compute b minus a, and then it's going to use that calculation to set a bunch of flags in the condition code register. And those flags will help us decide whether something's equal to 0 or one thing is less than another. And then we can make the appropriate jump based on which flags have been set in that flag register. The last piece we need as an instruction to make the jumps. All right, and now if we think about functions a little bit, they are very similar to these other things. They need some of the same things in that the way a function works, I'm going to get to a function call, and instead of executing the next line after the function call, I want to jump to somewhere completely different in the code execute a bunch of statements, and then when I'm done with the function, I want to jump back and then execute the next piece. We actually have everything we need already to pull this off if we wanted to do a little bit of extra work, but x86 provides us with some cool instructions to make this pretty easy. Easy is not the right word. This is a challenging topic. Here, let me just pull these up. So some of the things that we'll be looking at today, we're going to take heavy advantage of the stack. So we're putting all kinds of things on the stack. Parameters, return values, the local variables, and they provide us with a stack pointer and a base pointer to help make this go smoothly. A bunch of new instructions. We'll call the function, leave, return, push and pop. These are the major ones we'll be using today. So let's take a look at an example function and talk about some of the things that we'll need to consider as we start diving into what makes this complicated, how can we be organized about it, and actually be successful at understanding what's going on behind the scenes at the assembly level to implement function calls. So here I've just got an example program, something quite simple. I've got my main function right here. It's going to call sum as a function, give it some parameters. Up here I've got my definition for sum. It's going to accept those arguments right there, create a local variable, compute the, oh man, that's supposed to be a plus. Hold on, let me go fix that. All right, got it fixed. So it's going to compute the sum when I add together the two parameters x and y, store that in my variable total, and then return that. And that's it. That's all this is going to do. So we're going to start out and talk about all of the issues that we're going to run into as we try and figure out how to do this in assembly. And some of those things, first some vocabulary. So I'm going to be calling one function from within another. So main is the function that is going to be calling sum. So it is the caller function. And we'll see there's a bunch of responsibilities that the caller has to set things up for the function call. And then sum is the callee. The callee is the function that is actually called. Okay, I hope that makes sense. Just some words, some vocabulary I'll be using throughout the lecture today. And now we've got 7 issues here that we need to address. Number 1, how do we actually call a function? We actually have enough tools right now. We just need to jump somewhere else in the code, do some execution of those steps, and then at the end of that, we need to jump back. So we could store the return address, the next instruction on the stack, just use jump instructions. We could make this work. Next, how to return control back. Yeah, we'll need to jot down the return address. We could make this happen, but there's some conventions that x86 tells us how they're going to go ahead and take care of this for us. So for reading assembly code generated by a compiler, there are rules that it follows, and that's what we're going to be learning today, so we can see how things are taken care of. And then how to return values. So right here I'm returning a value. I need to know what to do with that. How do I go ahead and make sure that main has access to that value? How to pass parameters. So right here I'm passing in a 1 and a 2. I need to know how to take care of that. This is going to be the responsibility of the caller to take care of those. And then how to allocate space for local variables. This one's going to be, so like right here I'm initializing total. This is going to be one of the responsibilities of the callee. And they're going to get their own little space in the calling convention where these things are taken care of. Let's see. How to access parameters and local variables. So we'll have parameters here, x and y. We have local variables total. How do we access those? Where are they stored in memory? And then finally, how to deal with registers. So on an x86 machine, we only really have just 6 general purpose registers. And there are rules that assembly uses as they deal with how do I share between a caller and a callee. Like, for example, if main here is using all 6 registers and then it calls a function, and the function wants to use those registers, and then when it gets back, it may have changed the values. So we need a set of rules to deal with making sure the registers are in the right state so that everyone can share them and not overwrite someone else's data. All right. And just a couple thoughts. My next example as I go through has a lot of very specific details. I put in exact memory addresses. I wanted to do this for the very first example because a lot of the questions on the homework or on the exam are going to be like, where is this value stored in memory? And I expect the memory address. I'm only going to do this for the first one. I think it's a lot of detail that that actually makes it a little more confusing when we get to harder examples to understand the big picture. And I think what I want to do is do one in-depth first look, and then take a look at the rest of these issues, 3 through 7, at a much higher level. And I think you'll see in just a second why basically I just don't have enough screen space to put down all of the addresses when I start making slides for this stuff. So hopefully that's not too confusing. This is one of those things, and there's just a lot of pieces. We'll have a stack, we'll have instructions, we'll have registers, and as time advances, as we go through the steps, these things keep changing. And so having a system, let me pull this up, a system where each piece of what's going on is designed to be fit into a certain part of the calling convention to just keep this organized. So this calling convention says that there's going to be basically, let me walk through this slide. This is going to get broken down. So each function call is going to get broken down into a number of pieces. So in C, I've got a function call right here, sum 1, 2. This is just one line. This one line right here is going to get broken down into 5 large blocks, maybe 30 lines in total if it's a complicated function call. The blue ones here are the caller responsible sections. So the main function is going to be responsible for the startup or setup block, and they're going to take care of things like, I need to know where to come back to. I need a return address. I need to store that return value somewhere. I need to be able to know that. If I've got any registers that I'm using, some of them are my responsibility to just make sure I've got a backup copy, store that on the stack for all the information I need. Okay, then the orange text here, all of these are callee conventions. So I'll come back in a second. And after the function is done calling, I need to go ahead and restore the registers that may have been overwritten by the function call. I got to deal with the return value and put it wherever I really want it. This example, I'm storing it in a variable called s. So I need to make sure it goes in the right spot. And I've got to return to the next instruction. All right, so then the inside the function call, all 3 of these orange boxes right here are this just one line right here. This is the actual function call. Inside of the function call, I've got the function body. This is all the stuff that's up here, right? Inside the functions line 2, 3, and 4. And the prologue and epilogue are things that don't appear in C that we need to take care of. The prologue is going to have basically be responsible for saving all of the registers that I need to restore. So it's going to save some registers in case I want to use them. Then it's going to take care of making space for the local variables, so total here. It's going to take care of making sure the stack is organized and store the base pointer so I can figure out where this number 1 and number 2, my x and y, where they're stored, because they have been stored by the caller. Local variables total here is going to be responsible. The callee will be responsible for that in the prologue. Okay, and then in the function body, I do all this stuff. And then when I'm ready to return, I need to make sure the stack is like cleared off. I remove all of I've stopped using it. I rewind my stack pointer to the top of the previous stack. I grab that return address. I store the return value in the right spot. And I need to put the registers back that I've stored up here in Prologue so that they're ready to go for the caller. All right, yeah, I think, so there's a lot of pieces going on. Our book doesn't have a picture that looks like this one, but it does take all of the individual sections as we go through those list of 7, this list of 7 things. They break it down and do a pretty good job. I'm going to go ahead and try and point out which section, which box they go in as we go through these things. All right, so let's take a look at just that very first one on my list, 1 and 2, how to call a function, how to return from it. So I've gone ahead and I've simplified this. I took out the sum and I created the absolute most simple function I could think of. So first, I don't want to return anything. I just want it to be void. I don't want to have any parameters to deal with, no arguments, no parameters. So empty parentheses. I don't want it to do anything. The function body will be blank. I'm just going to return. And then I've got the most simple possible main function that just calls my function and then returns. Okay, so this is what I'll be working with for this how to call return piece of this lecture. Over here I've got just some example of instructions, and these are a little more generic. I didn't actually fill things out. So for the main block here, I've got some instructions, another instruction, call to function. So this is the real actual command that we would use to call a function. And then somewhere else in memory up near the top, all of the code is at the top of the memory. Memory is just one continuous block, so that's kind of why I wanted to like put it all in one blue box right here. But for the second example, it totally won't fit. So this is the only time we're going to be looking at the entire memory all in one piece like this. But yeah, my function here has some instructions, some return. Okay, and we'll come back and talk about what those instructions are in a little bit. And then at the very bottom of memory, I've got the stack. Remember, the stack is going to grow up towards smaller numbers. And I've just got at memory address FA8, this is the top of the stack. There's some data here from main or whatever when I get to the point when I call the function. I have a special register that stores the stack pointer. So over here in the like comment side of things, I've got ESP stands for stack pointer. This is just going to hold the topmost used address. Also over here, I've got the instruction pointer. And we start off, the instruction pointer is going to be pointing to the very first instruction in main. And then let's see, I've got two more blocks I'm going to bring in. Just to keep track of things that are going on in the CPU, I've got my registers over here. And again, the instruction pointer is pointed to that very first instruction at 100. The stack pointer is pointed to this top of the stack at FA8. And remember, the instruction pointer holds the address of the next instruction to be executed. So right now, if it's pointed here, that means I have not yet executed instruction 1. Okay, so I go ahead and do that. I execute instruction 1. It moves down. It's now I'm pointed at instruction 2. Move down. It's pointed at instruction 3, the call function. And then it's going to move down and point to there. Then I execute this. So the instruction pointer points at the next one. So I've got this updated here. I'm now at 10C. Got the instruction pointer pointed at instruction 3. This is what I'm going to call. This is where I want to come back to after I call the function. So I need to take note of that. And I didn't do anything to the stack. That's still the same right there. Okay, so when I call the function, the first thing I'm going to do is I need to actually return. So I need to know where to return to. So I need to grab this return address, the address right here, 10C, so that I know what to do when I'm all done with the function. That's what needs to go next. I need to put this value, 10C, into EIP register. Okay, so to do that, this is what happens when I do the call instruction. This is what's it's taken care of for me by this. But it basically does just a push of the instruction pointer onto the stack. So if you remember, push instruction is the same thing as basically making more room. So if I want to add room to the stack, I need to move the stack pointer, and I need to move it up. Okay, so that's going from a large address to a smaller address, so I'm going to be subtracting. And because the registers are 4 bytes, I need to subtract 4. So this will make space on the stack. And the next thing I can do then is move the value of the instruction pointer right here, 10C, into the new address where the stack pointer is pointed to, FA4. So if I do that, there it is. It's now stored on the stack. So this step or these two, if you can think about it either way, are what happens when I use call. This just happens automatically. It's just going to take care of both of those steps. It's going to make space on the stack, increment the stack pointer, and then push that return value, not the return value, the return address onto the stack. Okay? Then the next thing it's going to do, call also takes care of this for me. It's just going to jump to the target. So this function call is call function. This is a label in assembly. So right here I've got my label. It's got the colon to tell me it's a label. It's going to jump down to the very first instruction of this function. So it's just basically an unconditional jump to a target, which is a label in this case. So now I've got my instruction pointer pointed to the next instruction I'm going to execute, 204. I've got it updated over here in the register, 204. Okay, so as I continue through, I do instruction 204, I do instruction at 208, 41, and 42. I get to that return statement. At this point, the instruction pointer will be pointed somewhere beyond that, but it's never going to execute this one. We're about to do the return. So, and remember, it's always pointed to the one that we are about to do, not the one that we're doing at present. So we read this, it gets incremented, and then we do it. So when we get to the return statement, RET, what that's going to do is it's going to return control, and essentially this is just going to be a pop of the stack. So a couple ways we can think about this. When we pop something from the stack, we grab this value at the very top, the 10C, and it's getting put into the instruction pointer. So let's see here, did I do that right? There we go, 10C just got moved into instruction pointer. Up here I've got my new instruction pointer pointed to 10C, the instruction I will execute next after I'm done returning. And it also decrements the stack pointer, so this gets moved down. This value doesn't get overwritten, it's not zeroed, it's still here, but this is now the top of the stack, so this is considered memory that's not actually allocated at this point. And the very next function call or the very next push or pop will overwrite this. Anything else I need to say here? All right, I just wanted to simplify this. I took out a bunch of stuff and redid my memory model. There's not going to be space for the more complicated examples to put everything here. So when I do a call, I'm going to push the return address onto the stack. So right now, here I've just got a big blue box for my stack. It's got a bunch of stuff in there for main. When I call a function, the first thing that happens in that the caller setup is that we push the return address onto the stack. That moves the stack pointer up. So I'm not going to keep track of what address this is anymore. I'm just going to use a little arrow for you guys. The next thing that's going to happen is we're going to jump to the target, and then that function is going to run. It's going to use the stack for whatever it's doing. It's get its own frame. And I've got this color coded here. The return address is going to be technically considered part of the main stack frame. And the caller is going to do what callee is going to do whatever it needs to. And then when it's all done, it's going to remove all of this stuff, return the stack pointer to point right at this return address, so that when I execute RET, that stack pointer needs to be pointed at the memory address with RET. And just to note, I've got my arrows pointed to the very top corner of the box, top left corner. I like to think of this as there's actually a whole bunch of lines, because this is a multi-byte instruction, so I'm pointing at the top byte. Just my personal little preference as to how I place the arrow. It's actually a pretty common convention, so I like it. Anyway, once the stack pointer is returned to this, so this is the epilogue part of the callee caller convention, is to make sure that I remove the move the stack pointer back down so it's pointed at the return address, and then I'm going to pop this. It goes back into the instruction pointer, and we carry on. So the things we saw here, we've got the function call in the startup here. That's going to take care of pushing the return address on the stack, and then in the epilogue, I've got to do two things. I've got to make sure that the stack pointer gets pointed to the return instruction, to the return address. And then when I call return, it's going to go ahead and jump back to and return control flow to the caller. All right, let's actually, I'm going to pull up some code and let's actually take a look at this exact function in assembly. One sec. All right, so I've gone ahead and coded this up and just gone ahead and compiled it into assembly with the -s option, so I can look at all of the commands. I'm looking at a file here. It's got 74 lines in it. So just as you read these, a couple of things to note. Anything that begins with a period, like this .file, .text, .global, these are assembly directives or assembler directives. These are just text there that's to guide the assembler when it turns the real instructions into machine code. Okay, so if it begins with a dot something, we can probably ignore it, is the bottom line here. So the very first thing that we see here is the actual label for the start of the function. Ignore that, ignore that. And we've got some statements. This NBR32 is the fact that we're branching into this. And so this is for, I looked it up, I couldn't find a whole lot. But it's got something to do with the fact that this is the start of a branch or the end of a previous branch. Then there's a couple of instructions here that are dealing with setting up the stack for the call E. We don't actually do anything. This function does absolutely nothing. So it sets it up, gets ready to return here. Right there, it's preparing EAX with the return value, which then does nothing. Now NOP stands for no operation. And then it does the restore the stack. So this EBP is the base pointer. That's the next topic of the lecture, actually, is the base pointer. in preparation for talking about how we can figure out where all of the things, the local variables are stored on the stack if the stack pointer keeps moving. This is just a convenient way to do that. So it prepares it. We're done with it. It doesn't do anything. There's no op. It tears it down. And then return right there. So that's what this looks like. Ignore everything that begins with a dot. I'll be talking about the EBP in just a second and the returning in just a second. So that's what those are. And then when we go down and look at main, it's got a lot of the same things. It's a function. So we're beginning with, this is the beginning of a branch. It does this same pair of stuff to prepare the stack, the EBP, and then move the stack pointer into EBP, the base pointer. Same thing here. Every function begins with these two pairs of statements. Push EBP to the stack and then move the stack pointer into it. And then, again, it doesn't really do anything. It calls the function. Let's see right here, call function in line 37. And then, there's really no cleanup. It doesn't use any registers, so it's skipped all those things. Instead, we just move 0 into EAX, right there, that 0, and then we return. And again, the last thing in function is we clean up our stack to get ready for whatever comes after it. So we pop the base pointer again. All right, so that's pretty much it for this one. There's a lot of stuff here. If you go ahead and delete all of the lines that begin with a dot something, dot long, there's not that much to it. It's the blue lines that are the x86 code that's actually getting compiled. The rest of these are just things that help the assembler turn this into machine code. All right, let me pull up my next example. I'll be right back. All right, next up I want to just talk a little bit about return values. So I went ahead and made a bunch of slides for this and a new example. So I've taken my really basic function, and instead of just having it return nothing, being void, I'm going to go ahead and just have it straight up return a number. So all it does is return a number. I change the return type here. And then in main, I'm just going to reserve some space for that answer. When we go look at the assembly, I want to be able to spot this line right away. And they're not actually going to use a nice, neat variable name. They're going to give me a register name. So I want to stick something in it so I can spot that $1 and know where this is going. And then I'm just going to call the function here and put the answer into my answer variable. Okay, so as we do this, there's two methods that we'll see are part of the function calling call convention for x86. The first one is for larger data types, for structures and things that don't just fit in a register. And that's to use the stack. If it fits in a register, then it just uses the EAX register as the return value. I'll show that in a second. My example here, I'm returning a number. This would fit in the register, so this will be done by the register version of return values. But I just want to walk through the example with what would happen if we wanted to return something on the stack. And as a lead in to talk about some of the stack management issues that we're about to run into. Okay, so I've got my function here. I've got some abbreviated assembly code and a picture of my stack here. So the first thing that happens is we're going to move 1 into EAX just so I can spot which register it's going into. And that's reserving space for the answer right there. Okay, next thing we're going to do is I need to make space on the stack for the return value. So I'm going to go ahead and make some space. That's this line right here. Subtract 4 from ESP. So the stack pointer, subtract 4. Remember, 0 is up here, big number is down here. So by subtracting, I've just made available some space. I didn't actually put anything in here yet, so I just put it in my little schematic as return value. And then when I call the function, the first thing this does is it's going to push the return address onto the stack. So the return address gets pushed, the top of the stack is now up here, and we jumped into the function. Now the function needs to be able to know where to put its return value. It knows that it's got a 42 that it has to stick somewhere in the stack. And so right now the stack pointer is pointed right here, and the return value needs to go right here. This is 4 bytes. That should be a positive number. Timeout, let me fix that. All right, got it fixed. That should be 4 bytes greater than wherever the stack pointer is pointed, because these are bigger numbers down at the bottom here. So I add 4 bytes because that's how much space is reserved for the return address. And that's where I'm going to put the return value. So I just move immediate value 42 into this spot right here. And that's all I need to do. Then I can just return. This return statement will pop off the return address. And I think I've got one more slide, where I put in the 42. I just want to mention too, before I jump into that return, that there's a whole bunch of space here. If this were a more complicated function, the stack could be used to store other registers. It could be used for intermediates in computations. It could be used for local variables. There could be a bunch of stuff up here. And the stack pointer is going to always point to the top of that. So figuring out where to stick this is not always going to be 4 bytes off the stack pointer. The stack pointer actually has to be pointed right here for it to be 4 bytes away. So we're about to see the base pointer convention introduced in the next series to help deal with the fact that the stack pointer moves around. Now if it makes it easy to find where the return value is going to be. Okay, right. So then when I'm ready to return, I'm going to pop off the return address. And now the stack pointer is pointed to the return value. The very first thing that main needs to do after the function call returns is to take this return value and do whatever it wanted with it. In this case, it needs to store it in answer. I've decided that I'm using register EAX for answer. So it's going to move the data stored where the stack pointer points. So I've got the parentheses this time because I'm accessing this value. It's going to move that into register EAX. All right. So the things that we've added now are in the startup sequence. This is before the function is called. The caller, main, is going to need to reserve space for the return value on the stack, and then it's going to call. And then in the epilogue, after the function has done all its work, it needs to put the return value in the right spot, and then we can call return. And finally, during the cleanup phase, the caller is now responsible for taking that value off the stack and putting it wherever it really needs to go. All right, the other way that we'll return values is to just use a register. And this is the first choice if the answer fits into a register, if it's either a pointer or an integer or anything smaller than that, we'll be going ahead and just using EAX as the default place where return values are stored. So this is what's really going to happen when we go look at this function in assembly over on a CSL machine. So first, we're going to be, let's start here in main. I'm going to move 1 into a register. I switched to EBX because EAX is going to be the return register. It's going to get overwritten. It's not going to be preserved. So as soon as I call the function, EAX will get overwritten. My 1 will be done. So I'm going to use EBX now for my answer. So answer is now in EBX. When I call the function, that call line right there is going to push the return address, which is that movl line, onto the stack. And then I jump into this function. First thing that happens is instead of using the stack for the return address, if I'm just using a register, the only thing this function really needs to do is move 42. So it'll have a frame here. If it's more complicated than that, the stack will use that space for local variables, for temporaries, whatever it needs to store registers. But the only thing this function actually does is put 42 directly into the return address, which is the EAX register. So it just moves it straight in there. And then when it returns, it just pops the return value off. The stack pointer goes back to pointing at main. And then I have to deal with my result. So I move the value from the return location, EAX, into my variable. Answer is in EBX. All right, let's go hop over and take a look at this in code. Sorry, I should have done this earlier, but if you guys are following along at home, if you've downloaded all of the functions from the code directory on the Canvas page, you can go ahead and pull up function 03.c. I'm compiling this with the -s option, and that will create the function 03.s file with all the assembly in it. I did get a warning when I compiled this one because I'd never used answer, I just set it. And then to pull up both files side by side in Vim, I'm using the $O option and the wildcard star here to capture both the C and the S endings. So when I do that, the function I've got over here, I've already gone over this. I'm just replacing the return nothing with return 42 and change the type to int. I'm storing that in answer. So I'm setting answer initially to 1, so I should be able to spot where it's reserving space for answer in main. Let's see what this really did. So up here, I've got a lot of stuff going on. I can ignore all of the assembler directives. If it begins with a dot, I can ignore it. So here's the beginning of my function, and then down here is the beginning of main. So let's start right there. We see these first 3 blue lines are pretty much the same for every function call, where it's end of a branch, I'm pushing the base pointer, and then moving the stack pointer into the base pointer. I'm going to address that very soon, I promise. All right, and the next thing we're going to do, it's reserving a bunch of space on the stack. So it's subtracting 16 from the stack pointer. So reserved a bunch of space. And then we are moving, yep, that's to have space for this stuff right here. It's moving 1 into EB4. So EB4 is the base pointer. So this is just an address related to the stack. So it's reserving space for the answer on the stack and putting a 1 in there. Then it's calling a function. And that memory address right there is where it's sticking the return value after it returns. So when function is called, the return value is stored in EAX, and that's getting moved into the memory location for answer. So that right there, -4 EBP, matches the -4 EBP. So this is a memory location on the stack. I see the parentheses, I'm accessing memory. All right, and then this is the return 0 line. We move 0 into the return register and then leave the function. Return. Okay. Oh yeah, leave. The leave instruction is going to take care of when I reserved all of this space on the stack, the 16 bytes there from the stack pointer and subtracted it. That just restores the stack pointer, and then return will jump back to the whatever function called main. Okay. Then when I look at my call function, if I jump up into the function, I can see that I've got those same first 3 lines, NBR32, push the base pointer, move the stack pointer into the base pointer. That's just to set up the frame. Then over here, I'm getting ready to put something in, yeah, right here, move out. I'm moving 42 into that return register, the AX, and then I do all my return stuff. I pop off the base pointer, that's to like clean up the stack, and then return. All right. Hopefully that's clear. There's a lot of stuff going on, a lot of pieces. It's pretty much a foreign language the first time you look at this stuff. I hope going through some of these real examples is helpful. Yeah, let me go make some slides and talk about this whole base pointer issue. I think that'll clear up some of the questions you might be having. One sec. All right, so the next 3 pieces all kind of go together. I want to introduce the idea of the base pointer as a way to have a consistent starting address to look up locations on the stack. So if I'm pushing stuff on the stack or popping stuff, the stack pointer changes. So to use the stack pointer as a way to get to a particular spot, a particular place where I may have stored X, for example, it changes throughout the whole thing. It makes it very confusing, very complicated. So we've introduced the idea of another register, a special register known as the base pointer, %EBP, to keep track of the bottom address of the stack. That's never going to change during the execution of a function. When we call a function, we get a new bottom of the stack. So I just want to sort of show you the motivation, walk you through this with an example. And the example, I need some more stuff on the stack, so I'm doing passing parameters at the same time, kind of. Hopefully I won't confuse people by doing 2 things at once. So here's the idea. I've got some new code. I'm now calling a function that has some parameters, 2 and 3. Just want to keep it simple. I'm going to have int x and int y, and I'm going to return their sum. All right, so let's take a look at what's going on. So at the very beginning, I've got my base pointer pointing at the very first memory of the stack for the main frame. The stack pointer, of course, pointing to the top of the stack as always. So the first thing that's going to happen is I'm going to start doing the caller setup. That's going to involve pushing a return value. This is going to reserve some space if we need it. I've got some extra stuff that doesn't match this program right here. This is just going to use the EAX register, but if this were returning a structure or something, I would have a return value. I might push some parameters on the stack. The parameters get pushed in reverse order, so it's going to push y first and then x. Basically, they go right to left so that the offsets when we read them are increasing. All right, and then when we get to, then right before the call, we need to push the return address. This is actually that call statement, call instruction in assembly. We'll push the return address. And then the next thing we do is sort of some stack management items. So some stack management items. In this case, I'm going to be moving the value stored in my base pointer register, which was the address of the bottom of main, and I'm going to push it on top of the stack. And this is going to be my very first bottommost memory address of the stack for my call E frame. And then I'm going to take this base pointer. This is a register over on the CPU. This one is memory on the stack. I'm going to put the value of the stack pointer in here. So essentially this is now pointing to the exact same spot. So let me click. What I've got stored in the memory is the old stack pointer from main, old base pointer. Yep, the old value down here. So that I can, when I'm done with main, I can return this, and then I still know where the bottom of main is for all of my offsets. And got this pointed up here. So the value here now points to the same location as the stack pointer. It points to this memory address. Okay, now here's the motivation. If I keep using this, if I add a local variable, then I want to do some math. Suppose I want to add parameter 1 to that. If I were using the stack pointer, let's see, this is 4 bytes. So this would be right here is 4 bytes bigger. There's an extra 4 bytes bigger, and there's 4 bytes bigger yet. So that's 12 bytes larger than the stack pointer. I do some math. And then I add another local variable, so I added more space. And now if I want to use parameter 1, again, instead of being 12 bytes away, let's see, now there's 4, 8, 12, 16 bytes. So the memory address to get to this same parameter keeps changing every time the stack pointer moves. And that's going to happen throughout the execution of like any reasonably complicated code. It's going to push registers there to store them while it's doing other computations. We only get 6 registers, which is kind of a small number for any sort of complicated computation. So that's the idea. I'm going to push the base pointer here, and now this base pointer will never change as long as I'm inside this function. It's always going to stay pointed at the same spot. And that means what I can do is say that parameter 1 is always going to be, well, there's 4, 8 bytes away from wherever the base pointer is. Parameter 2 is always going to be 12 bytes away. And no matter how much this stack pointer moves around, I can always use the base pointer to figure out where my parameters are stored. And same deal with the local variables, because right now the stack pointer points at local 2. If I add another one, stack pointer will point at local 3. But the base pointer is always going to be, well here, local 1 is going to be 4 bytes earlier, so subtract 4 bytes to get to local 1, subtract 8 bytes to get to local 2. I can always use the base pointer to have a consistent memory address for getting to all of the different pieces that I'm interested in. All right, let me see. I think I have to make some more slides. Yep. Yeah, the stack pointer can move anywhere. As I compute things that are complicated, it's going to be all over the place. And I don't want to have to worry about keeping track of how to get back to a particular local variable. Oh, right. And then when I'm all done, assembly provides me with this leave command. I think we saw that in the last example. This is pretty straightforward. All it's going to do is going to take the current value of the base pointer, which points right here, and move that into the stack pointer. That's going to bring this stack pointer down, deallocate everything above main's base pointer, and then it's going to pop the base pointer. So it's going to take the value here from main's base pointer and put it back in EBP. So now EBP will point to the bottom of main. This pop will move the stack pointer down and now points to the return address. And with this pretty simple convention, leave frees up the stack and gets us ready to return. So the stack pointer needs to be pointed to the return address before we ever execute return. Leave takes care of that for us using basically 3 simple lines. So, and we're going to see those 3 simple lines at the beginning and ending, well, of every single function that we... All right, let's just take a look at this code for a little bit. So here's the function, int x, int y, return x plus y. Great. Main, also pretty simple. I'm just calling the function. So let's take a look at this in assembly. Here, I'm going to start out looking at main, and I see I've got these same 3 lines I just talked about. I'm going to push the base pointer, and then I'm going to move the stack pointer into the base pointer so that they're both pointing to the bottom of the very first frame, the bottom of the main frame at this point. It does a bunch of stuff. At the very bottom, I'm going to leave. That instruction is going to restore, it's going to take the value of the base pointer and put in the stack pointer, and then pop off that base pointer, and then makes it safe to call return because I know the stack pointer will be pointed to the return address when I do that. All right, so now if we take a look in the middle of this, what's going on here? Here I'm creating space for answer. There's my $1. It's my clue. I'm using a value on the stack that I've reserved. Let's see. Yeah, right here I've subtracted 16 from the stack pointer. This is going to reserve a bunch of memory. Remember, we're subtracting because the stack grows up. And it's just going to say the answer is now going to be stored in this location right here, 4 bytes above the base pointer. So all local variables for like this answer is a local variable, are going to be in relationship to the base pointer. So -4, then -8, then -16, depending on how big they are, of course, but for integers. All right, then the, let's see, the setup for the caller setup for the procedure call, I'm going to be pushing the parameters onto the stack in right to left order. So I push a 3, then I push a 2. So there's that immediate 3, immediate 2. Both of those go on the stack. I've made sure I've got plenty of room on my stack by reserving 16 bytes right here. It reserved slightly more than I needed. Some of that is done for memory alignment. I'm not going to go into more detail on that right now. They reserve some extra space. Sometimes it's wasteful. And then we call the function. So when we jump up here into the function, we're going to start off with pushing the base pointer. So that's going to take the base pointer. It had been pointed to the bottom of main, and it's going to just store that bottom of main address at the very first location of the func stack frame. Okay, then I'm going to move the stack pointer into the base pointer. So that's going to take the base pointer and actually reposition it so it points at the frame I'm looking at. Now from here, I can use that base pointer to grab the addresses from the stack. Now these are the local variables. No, Mike, these are the parameters, the 3 and the 2 that we push. So we push the 3 first, then we push the 2. So that x variable right there is going to be 8 bytes below where the current base pointer is. So it's still in the caller frame. I'm going to go back and draw a picture of this when I talk about parameter passing. This is my base pointer piece right now. But just to be clear, I'm grabbing a value from the caller frame. That's the parameter. The 2 here, I'm storing in EDX. I'm going to grab the 3, which was pushed first, so it's farther down, 12 bytes below. Push that into EAX. I'm going to add them together, so the result is stored in EAX. That's where I'm going to be returning this. I'm returning an integer, so it's going to use register EAX as the return location. All right, and now I'm getting ready to finish up. I've got the return value stored right here, so I'm going to pop off the base pointer. I didn't use anything else in the stack. There's no need to call leave. I just need to return the base pointer so that it's pointed to the bottom of main stack frame so that I can access the variables in main using the correct base pointer. And then when I return, that pops off the return value. The stack pointer is now pointed to the very top of main. And let's see, then when we return right here, yep, we're going to add to the stack pointer. So remember, the stack pointer is growing towards smaller numbers. By adding, that's going to remove the space that we reserved when we pushed this 3 and the 2 there. Okay. You know, I think I said this backwards a little bit ago. I reserved some space here, the 16, but then I pushed 3 and 2. So those are way actually higher than the 16 that I reserved a moment ago. Anyway, I've now reclaimed that memory. And then I've got my return result right here stored in EAX. That's going to be moved over into answer, which, as we said before, where I stored the 1 was 4 away from the base pointer. And again, 4 away from the base pointer here. And then move 0 is the return 0. So I put EAX as my return value. Leave will go ahead and move the stack pointer to the bottom location of the base pointer. Just clears up all the stuff, all the memory reserved in main for main stack frame. And then here on line 50, we return. All right, I just want to go a little bit into passing parameters. So I'm going to use the exact same example I just did, but instead of looking at the actual code, I'm going to be looking at pictures of the stack. I've got the code here on the left, but as we're passing parameters, we're going to be using the stack, and it's going to be the caller responsibility to put them on the stack. So I've got blue for my caller functions, and again, the sort of yellow color for the callee. So here's what's going on. We're looking at main right here. First thing we do, we push the base pointer, and then we move the stack pointer into the base pointer. So both of these are pointed at the exact same bottom of the main stack. All right, and then I'm going to reserve some space. So this is going to reserve some space for local variables. I'm just going to subtract 16 from the stack pointer, move that up. I'm not going to put anything into them. I'm just going to leave those blank. And then the next line down, I stored a 1 so I could figure out where my answer was. And that's going to be at 4 less than the base pointer. So the base pointer is right here. 4 less is going to be above it. So this is the address, -4 from the base pointer. I'm putting a 1 right there. so that I know where my answer is supposed to be. All right, and then the next thing I'm going to do, I'm going to push the local parameters, or push the parameters onto the stack, not local, push the parameters onto the stack in the caller frame. So push 3, push 2, they go right to left. So parameter 2 is actually going to be in the number 3, that'll be the number 2. They just get pushed on the stack moves up. Now, when I call the function, first thing that's going to do is push the return address onto the stack, and then we jump into the function here. So up here at the top, we're pushing the base pointer. Let's see here. So I've pushed the base pointer, and what's in the base pointer right now is the address of main's base pointer. It's pointing to right there. So it's going to store that right here so I can get back and restore the base pointer when I move back into main and still find everything. But I want to be able to use that register while I'm up here. Okay. Next thing, I'm actually going to put the stack pointer in the base pointer. So that's going to change the register to this address. Okay, so the first step was changing the memory to just save it. Then second step, change the address in the register on the CPU so it points to the right spot. Okay, next up, I'm doing a little bit of math. So over here we've got the move, and now 8 addresses above EBP. So my base pointer right here is pointed here. So 4 addresses above would be the return address. 8 is going to be parameter 1. That's going to be the 2. And then here 12 addresses above in EBP is going to be the number 3. So these are just the 2 memory locations where I've pushed those parameters, and it's now computing those based on the position of the base pointer. Okay, so it's accessing pieces on the caller stack frame, and we're just storing them in registers. The first one goes in EDX, the second was into EAX. We do the math so that the answer is stored in EAX. That's going to be the default return value for integers and pointers. And then we're pretty much done. So we're going to pop the base pointer. That's going to say grab whatever's on top of the stack, which is main's base pointer, and stick it back in that register, in the EBP register. So that moves it back down here. When we popped it, it's gone. We also move the stack pointer back down. At this point, we're ready to return. So we click return. We remove that return address. The instruction pointer goes back down to the location right after we have added or called the function. And the next thing it's doing is we're going to recover that memory. So this is the cleanup step from that caller convention. I have those 5 boxes I've got to set up. There are 3 boxes for things that callee does, the prologue, the function commands, what was that called? And then the epilogue. So this is the last part. I'm cleaning up now. So I'm just going to add 8 to the stack pointer. That's going to move it this way by 8 and basically delete those parameters that I no longer need. And then I'm going to do some stuff with memory. I've got the my return value stored in EAX. I'm just going to store that in where I've got my variable answer. So in this case, that was 4 above the base pointer, so -4, because I'm going to smaller numbers. Smaller numbers are up. I'm just going to store that in this memory location. And then I get ready to return. So I'm going to return 0. Return value goes in EAX. I just move a 0 in. And then leave will take the value of the base pointer and store it in the stack pointer. So that's going to deallocate all of that memory. And I think that was my last slide. Yep. All right. Hopefully that was clear. All right. I hope that made sense this time. I'm going to go ahead and put together another example where we're actually going to be reserving some space for local variables, and I'll be right back with that example. All right. We've already seen local variables just a little bit, but I want to create a section that's just strictly focused on dealing with local variables. I'm going to make it quick. We've seen this already, but I want to just highlight the local variable pieces. So I've got a function here. I changed it a little bit. It just declares 4 local variables, A, B, C, and D, gives them some values, and I'm going to return their sum. Main doesn't have any parameters anymore. I don't want to have that extra confusion there, just the local variables this time. So the way we're going to allocate space is, here, let me jump over. I've got the assembly code here. I cleaned up a bunch of those assembler directives, things that aren't part of the x86 for the function, just so it fits on the screen. So there are things missing. If you guys do this at home, when you pull up this slide, this code, you'll see there's a bunch of those other lines that I've been glossing over. But this got to be too big to fit, so it didn't look good. All right, here's the idea. I'm right now at the point where I have just called the function. I've pushed the return address, I've called the function, I've pushed the base pointer, so main's base pointer is now stored up here. We're going to be using that base pointer to figure out where all of the memory is located that I'm using for my local variables, so that's important. And we move the stack pointer into the base pointer. So this, we've stored it here, and we've got the base pointer pointed to the right spot now. Now to reserve memory, this subtraction from the stack pointer is what's reserving that memory. This is how I'm creating local variables, line 8 right there. It doesn't look like the reserved local variables, it looks like it's doing math. And that's exactly what it's doing. It's just doing math on the stack pointer. So when I click, it's going to move the stack pointer up by 16 bytes, enough for 4 local variables. All right, and then these next 4 instructions are just going to move those numbers 1, 2, 3, and 4 into the right spot. So A was 1, B was 2, using the base pointer as the sort of starting reference with an offset. So at 16 bytes above the base pointer, so there's 4, 8, 12, 16, I'm going to stick in the number 1. I did it all at once. Then the number 2, the number 3, and the number 4. So the stack pointer is up here, and I've just got the sort of relative address for all of these things also indicated here. These aren't technically registers. I was using this as like my arrow as the register symbol. Just want to point out where exactly all these things are. So 4 above the base pointer is going to be -4 right there. They're negative because the small numbers growing up, larger numbers going down, and the stack grows towards smaller numbers. Okay, then just to wrap up this function, what I'm doing here is I'm gonna, now that I've got local variables with on the stack with numbers stored in them, I'm gonna just take that, the -16, that's gonna be the 1. I'm gonna store it in EDX, and then I'm gonna grab the -12, the 2, store that in EAX, add those together, store the result in EDX. Then I'm gonna grab the next one, store that in EAX, that would be the 3 at 8 bytes away. We do more math, we add those together, store the result in EDX, and then again grab the 4th one, the 4 there, store that in EAX, and this time I want to store the final result in EAX because that's going to be my return value. All right, and then again this cleanup part. So this is the prologue part of the one sec. Yeah, I just wanted to go grab this slide, and I misspoke. The leave right here, the cleanup, this is the epilogue part where I'm preparing to return. I need to clean up all that extra memory on the stack that I used, put all the pointers back where they need to go, and let's see, that's done with the leave command right here. So I think this is where I left off. Leave will go ahead and say, put the stack pointer back where the base pointer is, and then just like that, and then it's going to pop the base pointer, so it's now pointed back here, and that decrements the stack pointer also, so I've got it pointed to that return address. Yep, so that's where those things go. Epilogue. I think I picked the wrong word the first time. Sorry about that. Hopefully that made sense anyway. All right. I feel like I've already talked about how parameters and local variables are accessed with the base pointer. I did that in like every single example for the last half of this. So I'm going to skip that as a separate individual bullet point. I've done it. And I'm going to talk a little bit about registers. So there are only 6 general purpose registers available on that x86 machine. And those registers are shared between all of the functions. So if main is using the registers and then it calls a function, those functions need the registers too. And so the way it's decided that this will work, to minimize the amount of extra work it is to like back up the registers for every single function call, is to just say that registers EAX, ECX, and EDX are not guaranteed to be the same. Functions are allowed to change those. And so if I'm a caller, and I've got something important stored in one of those registers, it's my job during startup to back it up, to put it on the stack. And I'm just going to use a push. Pretty straightforward. And then after the function is returned, when I need that value back during cleanup, it's my job to restore it. So I'm just going to pop those registers back off again if I need them. And then the other 3 registers, the EBX, ESI, and EDI registers, are guaranteed to be exactly like I left them when I call a function. So if I call a function, if I've got some important value stored in ESI, it's guaranteed to be there when I get back. That doesn't mean a function won't use it, that won't use that register, but those functions are required to make copies of all of those values. They have to store them. in their prologue. Then they can do whatever they want for their computation. But then before they return, they need to put those values back. So I've got sort of in my calling convention sort of format here, all the different pieces of a function call and all the different things they're responsible for. So to summarize for the register piece of it, EAX, ECX, A, C, and D, let's call them A, C, and D, are not guaranteed to be constant. So if my function needs them, I need to store them. Okay. B, S, and D, EBX, ESI, and EDI are guaranteed to be available for me. They're going to be restored. So if the function needs to use them, they need to make a copy. So basically there's 3 guaranteed to not change and 3 that are not guaranteed and may change. So that's just how the x86 has decided to deal with it. It's amazing the amount of different variations out there. Part of me is a little hesitant to say memorize this, memorize it, except that I'm going to have a test and I need to know that you guys understand. So there will be some specific questions that ask about memory addresses, that ask about what's restored and what's not. But there are some interesting things out there. There are machines out there that have hundreds of registers. There's one that has 540 registers, and every function gets their own little window of 32 registers. It can only access those 32, but they're all different. There are other places where there is no, it's a Wild West. Everybody is required to make copies of anything that you want back again. So it's depending on what you're doing, which assembly language you're working with, which architecture, different things happen. So, but in order for you guys to demonstrate to me that you've understood this, we're going to look very specifically at what happens with the x86 architecture and see in particular compiled with GCC with M32 options. So that's what we've got one very specific example. All right, I'm going to go grab one more slide and put everything that could possibly go in this calling convention diagram all in one slide and put it all together, and I'll be right back to wrap up. All right, guys, so I've got one final slide here, the giant summary of everything that happens in the calling convention, all the pieces in one place. And I think I've got the order right. I'll have to double check on some of these things. But here's the idea. During startup, the caller is responsible for saving some of the registers. I don't have a good example of that. To come up with an example where I'm using enough registers that I need to save them because the function needs them, makes for complicated functions that don't make good demos. I'll come up with something for a future lecture as maybe a review or just to highlight something when it comes up. Sorry about the lack of like a good visual there. Then also in startup, I need to push all the parameters. That's the caller's responsibility to make the parameters available for the callee. We're going to reserve space for return value unless it fits in a register. So by convention, first choice is to use EAX. That'll be for anything int or smaller or a pointer. But if I do need more space, or I'm returning a structure or something, we'll go ahead and we'll reserve space. And remember, to reserve space on the stack, we're actually growing towards smaller numbers. So we need to subtract something from the stack pointer. Then we push the return address and then call. All right. Then the next thing that's going to happen is we jump over to the function. And the function is responsible for a bunch of things too. They need to keep track of all of their stack management. So it's going to push the base pointer and move the stack pointer into the base pointer. So I keep track of where the old one was. And then I've got this as a reference for computing where all the local variables are and where all the parameters are. The functions themselves are responsible for restoring EBX, ESI, and EDI registers. So if I'm going to use those, I'll push them. I haven't had an example complicated enough where we had to like store registers. So maybe in the future we'll run across one of those and I can highlight that. Then just going to reserve space for locals. And again, to reserve space, it's the subtract from the stack pointer. Then the function body happens. Whenever we're done computing whatever it is, we need to get the return value ready. It's either going in memory on the stack or it's going in the EAX register. Those registers that I guaranteed, I promised I'll return them intact, I need to put them back. So if I push them onto the stack here, I need to pop them back off so that they are ready to go with their original values. So this is, I saved them, here I'm restoring them. And then to wrap up, the leave instruction does two things for me. It moves the base pointer into the stack pointer. That deallocates everything on the stack. It pops off the base pointer. That returns the base pointer to the base pointer location of the caller. And then we return. So that jumps down to the return value. And then finally, the caller is responsible for making sure that if they have dealing with the return value, so if it's in memory, they need to put it wherever it really needs to go. If it's in a register, do whatever they were planning to do with it. Any space that they allocated for parameters, they need to take those back. So up here, we were pushing them, push. To deallocate them, we're just going to add however many bytes we need to the stack pointer. By adding, that's going to move the stack pointer down and reclaim that memory. And then finally, if we're going to be using EAX, ECX, or EDX registers, we need to go ahead and restore them to whatever they had been. Again, we haven't seen an example complicated enough for this yet. Maybe in the near future we'll run across one. All right, I think this is turning into a long video. This has taken me almost 4 days to put together. I've got 83 slides. I'm going to wrap it up here. I don't even know how long this is. I feel like I've been talking for hours, but that could just be because I keep screwing things up, because this is complicated. I say the wrong thing and I reshoot it for you guys. That's it. All right, I'm going to cut this here. Have a great day. I'm going to immediately start recording the next video and hopefully get back on track a little better. All right, have a great day.